Excellent. I'm giving some notes on 1.3a. That's our unit on vectors. And let's talk about what we need to accomplish. So we have learning objectives for this section. First, distinguishing between vector and scalar quantities. So we'll talk about what those two are. Resolving a vector into its components, finding the x and y components of a vector. Next, reconstructing a vector from its components so that if we know both the x and y components, we could reconstruct what the vector is. And finally, carrying out math operations with vectors. All right, so let's start out by introducing two different types of quantities. The first one is something called a scalar. And a scalar is a quantity with only a magnitude. So if I was to tell you that 1 cup of sugar plus 2 cups of sugar, you would know that the answer would be, that would be equal 3 cups of sugar. All right, so scalars are quantities like cups of sugar, and they do not have a direction, they only have a magnitude. Whereas vectors are quantities with both magnitude and direction. All right. Well, let's list some of each. First, scalar quantities. Scalar quantities include things like the mass of an object or time, density, distance, speed, if I was to tell you that that I had a mass of 100 kilograms, you wouldn't ask, well, which direction is that? Temperature, for example. If it's 70 degrees outside, it doesn't matter which way it's going, right? It's just that's the temperature outside. By contrast, we have vector quantities. These include things like, well, if we look at distance, distance could have a direction, right? You could say, it's 100 meters. If I said, I have a prize for you, it's and you said, where is it? I said, it's 3 miles from here. Well, you'd have quite a search on your hands, right? Because you could be heading off from where you are. You would have to look 3 miles in every single direction, yes? And so that would give you this huge circle of area that you need to search for your present. Well, by contrast, instead of representing a distance as just a scalar quantity, in physics we have a vector quantity that corresponds, that's similar to distance, that is called displacement. And by this, a displacement is only complete if you represent both its magnitude, it's 3 miles, and its direction, straight east of here. Well, that's a lot more information, right? If I said you had a gift 3 miles straight east from here, you'd have a pretty good chance of finding it, especially if it's exactly 3 miles and you had instrumentation to help you do that. You could head 3 miles straight east and find your whatever it was, probably a pencil. All right. Speed also has a corresponding vector quantity. Sometimes the two are confused, but speed, like in your car, your speedometer, It only shows how fast you're going. It does not represent which direction you're going, but there is a vector quantity for speed that is called velocity. So a speed might be I'm going 5 miles an hour. A velocity would have to be I'm going 5 miles an hour north, or some direction representing either an angle or some way to represent which way that is going. There's some more vector quantities that you have to know that they're vector quantities. There's one we're going to talk about that's called acceleration. Force is a vector quantity, and we'll talk about more. But all right. In order to represent vectors, if I was to say that that in contrast to this 1 cup of sugar plus 2 cups of sugar is 3 cups of sugar, if I was to take a look at displacement and say, well, if I took a hike and I went 1 kilometer north, then I went, from that point, I went 2 kilometers south. Can you see that from the origin, from the point that I started, which would be like here or here, I would actually end up 1 kilometer south. So in vector math, you could say that 1 plus 2 is equal to 1, and that's screwy. So it's going to mean that we need some new math tools in order to represent or in order to manipulate and carry out operations with vectors. All right. The first one is multiplying a vector by a scalar. So let's talk about that. All right. Well, let's start with a vector, and use a straight line to represent it. We'll call our vector vector A, and it's a displacement vector. Let's say vector A is a displacement of some amount, and it has an angle that we could represent here. If we knew, kind of where the horizontal was, we could represent this angle, maybe this angle at some, that looks like about 60 degrees, but all right. So we have this vector A, and we're going to represent vector A with the letter A. And what if I wanted to say, what is the scalar? So I have a question for you here. What is the scalar 2 times the vector A equal to? Well, I don't know if this is totally intuitive or not, but basically 2 times A is twice of A, right? So what we would need to do is we'd need to, I kind of have an idea of how long that is. We need to go at the same angle, all right? The same angle, and I have to go, twice as far. So 2 times A, 2A, would be a vector that looks like this. How about, I have another question for you. What if I was to say, what is negative 1/2 times A equal to? Well, it kind of makes sense that 1/2 times A would be a vector, headed up this way, that would be half this long. Negative 1/2, maybe that makes sense as well, that instead of going this direction, it would go exactly the opposite direction. So it would still be this way, but it might head back this direction, and it would be half as long as A was. This would be a vector that represented negative 0.5A. Right. So this is how we can multiply a vector by a scalar, just by scaling, I guess you'd say, the vector. All right. I have a problem for you. Let's work it out together. It goes something like this. A person walks 5 kilometers east. Then 3 kilometers north. Then another 4 kilometers east. Find their displacement from the origin. Well, the origin is something that we just defined. We say, all right, we're going to call, let's say this spot here, the origin. All right, I'll even put a little O next to it to represent that is where we're going to start. We can solve this problem graphically by drawing vectors, and in order to do that, we have to set up a couple things to start with. The first one is we have to set up some kind of a coordinate system. So we need to define which way are we going to represent as east or north or whatever, and it's kind of a standard coordinate system on maps that we would call straight up north, and that would make this direction here east. And so let's use this, but this is our own decision that we would like to use this coordinate system. All right. Next, we need to define some kind of a scale. So the scale is your own decision, how large of a scale you want to work when you solve vector problems graphically, but you need to stick with your scale. You can't change your scale halfway through the problem. All right, so well, I have these marks. I guess they're probably close to inches here, and I'm gonna set up that that 1 inch, this distance here. 1 inch is equal to 1 kilometer for my problem. All right, so I'm going to say 1 inch is equal to 1 kilometer. And then this problem really has a couple different legs of the journey, and each one of these legs could be represented with a vector. So let's draw this out. The first one is 5 kilometers east. So they start at the origin, they walk 5 kilometers east. Let's draw that. I would need to draw 5 kilometers east. All right. I'll say that's about east. Here's my 5 kilometers. Puts me about there. Next, they walk 3 kilometers north. So from this point now, my second vector would begin here. You know, in vectors, actually, we have names for these things. This is called the head of a vector. And this is called the tail of a vector. Kind of makes sense. All right, so let's also define this point as point A, let's say. All right, so they walk from O to A. That's 5 kilometers. And we represented it as a vector here that is 5 kilometers long. And it's headed east. Next, we need a vector that's 3 kilometers long, headed north. And so we are at this point here. We draw from the head of our first vector. We put the tail of our second vector at that point and draw a vector representing 3 kilometers there. All right, so this is 3 kilometers. I guess we'll keep our significant figures there from the problem. All right. And finally, they walk another 4 kilometers east, and I would just, let's call this point B. That's one of the points along our little journey. Another 4 kilometers east, we draw that vector, and it looks something like this. I'm going to stick with green here. And call this point C. And then the question asks, find their displacement from the origin. In other words, how far are they from the origin? That would be the distance from the origin, but displacement is a vector quantity. So they want to know not only can we represent this as a distance this far on our scale, but also a vector quantity is saying this. It's saying that what is the displacement, not only how far it is, but also what direction. And we can represent this with a vector that starts at the origin and points towards their location, C. This is the answer to our problem, this vector. And this vector is something that we call the resultant. So when we add vectors, the answer that we get is not the sum, like when you add scalar numbers, but when you add vector quantities, we call, instead of sum, we call the answer a resultant. All right, we're going to call our resultant R, which is very commonly used for the resultant vector. So we'll call that vector R. And I want to know two things about it. In order to define a vector, I need to know two things. I need to know what is its magnitude and what is its direction. So we're going to take a look at that. Graphically, I can measure this thing. I can put my ruler right on that, and I can say it looks to be 1, 2, 3, 4, 5, 8, 9.5 inches, which would make it 9.5 kilometers. So R is equal to 9.5 kilometers. But that's only half the story. That's like a distance, but this is a vector quantity. We also have to know its direction. So I can put my compass, this ruler kind of has a compass also with it. I can put my compass on here and read that this looks to be happening at more than 10, less than 20, right? About 19, maybe, if you can read this as well as I can. It looks to be at about an angle of about 19 degrees. So R is equal to 9.5 kilometers at 19 degrees. And a lot of times I need a picture to go along with my answer because this 19 degrees needs to be defined some way, right? And so this picture kind of defines that 19 degrees looks to be 19 degrees towards the north, starting at the direction east. So we would say 19 degrees north of east. Maybe we would define that this way. All right, excellent. Let's talk about adding more complicated vectors. What if we have two diagonal vectors to add? All right. So let's do this problem. What if we said this vector here is A, and this vector here, let's say, is B. And what if we wanted to find A plus B? All right. Well, in order to do this, we have to first pick an origin point and determine both the direction and the length of A. Now, this ruler has little wheels. I can just scroll right down here. First, I can measure A. It looks to be, I can measure it out to 2 inches and 2.7 inches. All right, so in the same direction, I can make a mark 2.7 inches long. Somewhere around there. Call that A. Plus B, if you remember from the last problem, the way that we add vectors is we have to take the second vector's tail and put it at the head of the first vector. So if I could just grab this vector and drag it down and place it here, that would work. But I'll have to redraw it. So I'll measure the length of this vector. It looks to be 1.9 inches. And then I need to have the same direction here. So I need to draw it parallel to that. And I'll draw 1.9 inches. And this will be vector B. So that my resultant vector, the answer to find A plus B, is going to be a vector that starts at my origin point and ends at the head of the second vector. So the answer to these this vector addition, is a vector that looks like this, that we might call R. And I could measure R, and then if I was to find, let's say this is horizontal, if I was to find this angle, then I could represent R as being, looks like 4.3 inches. So R equals 4.3 inches and then I could measure this angle. Looks right at 40 degrees. All right. Subtracting vectors. Let's talk about how to subtract vectors. Well, if I wanted to say, what is A minus B? What is A minus B? The answer to this is the same as saying A minus B is the same as saying A plus negative B, or negative 1 times B. And so the way that I would solve this problem is I would measure A and redraw it. Here I can measure A and redraw it here, starting at some kind of an origin, call that A. Measure B, but in order to represent negative B, we have to draw it going the opposite direction, equal in magnitude. So B, for clarity's sake here, maybe I'll make B orange. B, I would draw the opposite direction. So that would be negative B. And then my resultant, the answer to my problem, is a vector that starts where I started at the origin and goes to the head of the second vector. So my resultant vector would be this one here. All right. So it's important when you're subtracting vectors, you are just adding opposite vectors, or the second vector is the same magnitude in the exact opposite direction. All right. Next, your data booklet. Your data booklet has some equations that you can use on any test for vectors. And this is what it says. It says AX is equal to A times the cosine of theta, and that AY is equal to A times the sine of theta. These are in your data booklet. You should take a look at your data booklet and find where those are so that you know those tools. And these tools are used for a process that we call resolving vectors. So let's talk about that. And that is finding X and Y components. You see, this graphical treatment of vectors, although IB might ask you to use this, it's often beneficial to be able to work just mathematically rather than drawing out scale diagrams of things. And so you also have to understand how to use equations like this, how to use sine, cosine, to resolve vectors or to find the x and y components of a vector. So let's take a look at how that works. I'm going to draw a coordinate system here. Let's say we have an origin and we have some kind of a coordinate system this way. And in your mind, this space might have components that are like, we could call this the x component and this the y, like axes on the coordinate system. And we could draw a vector that is on this coordinate system and call it A. So I'm going to draw a vector starting at the origin. I'm going to call it A. And what resolving vectors calls on us to do is this, is to say, all right, well, this vector A is really a vector that goes both up and to the right at the same time. In other words, it goes both in the y direction and the x direction in the same time. And it goes some amount more in the x direction than in the y direction, right? It's more in the x direction than the y. So we could represent, just like we could represent that point that it points to with x and y coordinates, right? We could say that this vector, if you start at the origin, this vector points to a point right here, and that point has an x coordinate here and some kind of a y coordinate here. We could also say that this vector A has two component vectors. So if I was to say, well, I could replace this one vector with two vectors, one that goes straight across and call that A's x component, and one that goes straight up and call that A's y component. So I could replace A with these two vectors and they would give me the same result. These two are identical to this one by itself. And how could I figure out what the components of this vector are? Well, that's where these equations come into play. So if I know what A is, then I could find AX by taking A times the cosine of theta, where my angle theta is this angle here. And I could find AY by taking however big A is times the sine of my angle theta here. When you're doing this, you have to make sure that your calculator is in degrees mode because you'll be using degrees for your angle theta. My favorite way to check to see if a calculator is in degrees mode when I pick one up is I like to do the sine of 90, and it should give me 1. All right.